Okay. Yeah, this work is about the template-based data deduplication approach to support the causality analysis in a big data context. Okay. Okay, let's start by talk with some kind of eye teaser here. So what do you see in here? So I don't expect you to catch in a quick because this picture is meant to be hard to recognize it. Okay, here you see the some kind of small air part on the uphill looking down or somewhere. So, okay, that's it. Is this all the information that we want? Of course not. Okay, so from the picture, what we want to do as a tech investigator or the forensic analysis, we first want to locate object that relevant. And we want to actually restore the relationship among those objects. For me, actually, the rare part is a lateral movement state. So I just don't want to understand what is happening now, but I want to also restore the trail, how it came to here, and what it is trying to do for the future attacks. Maybe it will soon jump into its prey in the downstairs, like a goats. That might be something that we want to see. So the point here is that we not only satisfied with just seeing the object, recognizing it, but we also want to restore the whole context, which is the whole attack scene here. Okay, so let me see this problem a little bit from the different angles. So for me, actually personally, doing the forensic analysis is swimming in the big like ocean of the events. So actually finding a way with no clues, trying to find connect the ways to connect stats so that we can restore the whole context. In this picture, not all of the red dots, which are alert, highly suspicious, are the real alert that we care about, but also not all the green alerts in the lower alert score are the ones that we don't care about. Basically, it gives us the full pictures when we actually connect the dots and see the actual, find out the actual intention of the attackers and be able to see the actual trails came to here and the ways it is heading towards. So recovering the context or the chain of the activities that we say is some kind of need on-demand access to historical data for the forensic analysis. So this is, as a whole, the process is a very data intensive and computationally heavy process. And then what this talk is about, basically the causality analysis that automates the forensic analysis to help a lot of the many attack investigators out there. And then causality analysis restores the context around the system events. We are not just caring about one or two alerts. We see too many alerts these days. Actually, we want to actually connect the alert events around the alert, and then actually restore the context around these alerts. And the restoration of the context is a data intensive, computationally heavy. And our research question that we are asking here is that how can we store our data and serve it to the attack investigation in a timely and efficient manner? So before getting into the real talks, I want to share our a real world experience. As a research institution for the NEC, we prototyped the pervasive security intelligence solution, which is called the ASI, that collects a very detailed the scaled information, which include the file events, and then system process creation events, and the network events. And then we covers the variety set of the end hosts, which includes Windows, Linux, and Mac OS X, using the different type of information sources. Actually, we position our solution as most detailed and heavyweighted solution. Therefore, actually, our the interested customer segment is one who cares about their accountability, safety, and then be able to look up their databases. So we deployed our solution to our lab environment. So at the time of this research, it was about we covered the 100 hosts, but now we have more than about 200. But it is daily data volume was about 2 gigabytes per day, and which translate into the 80K events per second. And then in our actual estimation, in our research, actually, we could estimate that a mid-range server could scale about the 1,500 the hosts. But in reality, what we deal with is that actually customers who has a 10 or 100 times of these numbers. Therefore, actually accommodating this kind of the data pressure and then provide the timely service to the investigation is a very challenging task. So based on our experience with our deployment in our lab, so we could draw some number of the intuitions, basically. First of all, actually, majority of data that we collected are file events. Basically, about the 90% of data are the file read and write, and open and close and deletion events. And actually, the rest of them, 5% are process creation and process killing and that kind of events. And then the rest 5 is about the network events. I know that this varies the site by site, workload by workload, but this is general picture that we see here. So having said that, actually file is the majority of data that takes huge amount of storage space, but we cannot simply delete them because file access is the essential part of forensics. It is a food trait the left by the attacker in the persistent storage, and we really care about the file events. And second thing that we observed from our deployment is that, and more actually short-lived processes are there, because actually the computation power becomes stronger, and then computation becomes cheaper. Therefore, a lot of scriptings and piping and those kind of things becoming more and more user-friendly. Actually, it was very traditionally were supported by the Bash or the Python or Perl. And these days, actually, the Microsoft Office also supports Microsoft also begin supporting promoting their PowerShell infrastructure that which also supports the IPC by the piping and all those kind of things. Therefore, due to this kind of thing, we see lot of process creation and then process exit events in a short period of time. And actually, this kind of events actually involves a very static set of pattern repeated over and over again. So it first loads the libraries and then configuration files and resource files as it bootstraps the process and actually be ready for the actual work to be performed by the program. Okay, having that said, I want to go over the one very simple test cases. This is case for the Python example. So as you can see, this command line actually specified its application logic with its command line, running the simple web server. In its initial stages, actually in whole lifetime, we see about the 600 files are read for loading and providing a service. But across the whole Python program executions across our lab from a certain period of time, we see that among those 600 files, we see 700 some files are commonly accessed as a part of its bootstrapping process. After finishing its initial phase, actually it begin touching its logic specific files the files related to the HTTP server, or the resource files etc host or resolve.conf. That is a typical pattern that we see. So that what we see from here is a huge repetition of the static setup, fixed set of the library or configuration files referred during its bootstrapping. So simple idea that we can think of here is that why don't we then make the template for this kind of set of files and make a single pointer to that template and make them actually referred over and over again for the future executions. So let's say we have 1,000 Python executions. Then what we're gonna have with the raw data is going to be about this amount of the data pressure, the entries to the database. This is really a serious problem. This is too much duplicated data. And then as we said, actually with the templates, actually we can make it much smaller. Just make one template with 367 and then one for its reference. And it can just simply repeat it 1,000 times. This is huge reduction that we can do it with simple math. And then this brings us to the simple question. Why don't we simply use a simple a data compression? So we have a ggip, xg, a lot of good data compression algorithms out there that we can use. But the problem here is that forensic analysis has its own a trait. Basically, it needs to, as I showed you before, actually when I do the forensic analysis, I jump around back and forth to future time X and time Y and things like that. Therefore, we need well-supported navigation, efficient accessibility to the data. So if you compress the data into the static archive, the compression of the certain time takes some time. That kind of delay really hinders the usability of the forensic analysis. Furthermore, our service, Causality analysis, try to automate the process and then this will expose a huge usability problem. Having that said, actually, I want to introduce our system design and workflow, how it works in action. First, we want to talk about how we generate the templates. This is kind of the very it is really important to have the sound and then efficient template to be applied to the real world. Okay, first of all, actually, our data collector caches the read-only files for the given time windows. This is tunable. We set from the 1 to the 5 seconds. So we only collects the read-only files accessed in its bootstrapping stages for a given defined the time window. Okay, so and then data collector actually stores the frequently accessed pattern for a given processes. In this case, process 1 has the file 1, 2, 3, 4, and process 2 has file 1, 2, 3, 5. And this file access pattern is given to the template learner. So from here, we want to build the compressible file access pattern on the fly. This is some of the challenge that we want to address later. Having that said, we actually generate the template with our template learner in the action. So for actual data coming in, our reducer that which implements the pattern, like the finite state automated based pattern matching algorithm that matches and translate them into the simple actually the optimized compressed data set. So upon a causality analysis later on, actually looking up the database and then make another level of indirection that will restore the original data. Okay, as I mentioned, actually the research and the technical challenge lies in the implementation of the template learner. So what actually the challenge here is that online analysis against a high volume of the streaming input and generate the sounds template is kind of like a daunting task. So this is a simple one-line formulation of the problem. What are the set of the read-only files accessed across a different process initialization? We are not just saying about the 10 or 20, but we are saying about the a lot of processes created from the hundreds of or sometimes thousands of processes. I think consuming that kind of the workload on real time is very, very challenging. Okay, and we can see this as some kind of the different problem. We can transform this into the very well-known problem, which is saying that market basket problem. We can see it as what are the set of the product in the market basket. They put the different customer put in their basket. This is very a well-formulated marketing problem because they want to also know about the customer who buys A and they also buys the B or C. That is a kind of well-formulated marketing problem. So we want to reduce and transform this problem into this well-formulated the frequent pattern matching problem. And then the algorithm of our choice is the epic growth algorithm, which is a cutting-edge solution, state-of-the-art solution in this domain. So yes, here's a brief introduction about how does the epic growth algorithm work in action. It works in the two stages. First of all, for a given data set, it tries to build the epic tree construction, which is like a linear algorithm that works in the order of the ON, time complexity ON, where the N is the number of distinct files that we have in here. For a given actually the table input as a table in the left, actually we want to generate the tree based on its frequency across the different processes, file access from the different processes. Second stage of it based on this tree constructed from the previous stage, and actually it is about actual stage that frequent item set generations, but its complexity is the exponential to the depth of the tree, which in our case actually, as we see from the depth of tree is you can think of as roughly the number of the read-only files actually referred during its initial stages. In previous case, Python, it was order of 100. In some programs, it is easily exceeds the 1,000. So actually, dealing with this complex problem in real time is really challenging. Therefore, we need to come up with some couple of some like optimization approaches to tackle this thing without compromising the accuracy of our approach. First approach is that based on our also data observations, we want to pass the prune which are less relevant to the actual like relationships. So from our data set, what we saw was that a lot of edges that defines the ordering relationship between files, not the files itself, are relevant to the actual data volumes. In our case, actually, the Perl, 62% of edges, which defines the relationship between the files, only contributed 0.2% of data volumes. In the case of the Python, the situation is even worse. 97% of them only contribute to the 0.3%. And actually, and the second intuition that we want to leverage is that many items appears in the group. So what we see is that once the use touch this file, you can easily expect the next file is going to be B and C and D. They comes in a group. So after we eliminating the unnecessary edges, it is more easier for us to merge those nodes in a single group. This is our example case for the date process. This is the process that we've seen. And then actually each nodes are besides the root nodes represent the file. Edges are represent the frequencies that we've seen from the data process across different machines. And then actually their percentages is about the decreasing order from the top to the bottom. Okay, from here, as you can see, there are some redundant edges, like with the very few frequencies from the A to C and B to D and C to D. Those are very small compared to the other edges. And this is again about the C came after A and about the D came after B. So this is not about the file A or C, but they're like orderings. So we feel safe to remove them, making the tree simpler. And then if you see it from this stage, you can see that all of nodes and edges connecting them are having a more or less same like a frequencies. In this case, they are in the certain threshold boundaries. Therefore, we feel safe to merge them into the single node. So in this case, after all, what we did is that from the depth 4 of this tree, so making it to the depth 1 tree. So now we want to evaluate our performance of our system. So yes, this is a basic setup for our evaluations. So we installed and set up the ASX system and NS Labs America. So the systems that we collected the event log are 75 hosts, and then one trace time was given for the collection. So these are basically the research questions that we were asking: how effective our approach to data reduction, and what is the impact of our the accuracy of the system dependency analysis. And research question 3 and 4 are about the effectiveness of our modification of the FP approaches. Yeah, this is the metrics that we used for our evaluation. And then as you can see from here, so we also first evaluated our reduction gain for different type of the host. Actually, what we want to highlight here is that our work especially work well for the data analysis and data processing tech, which involves a lot of the process creation and then end events. And then application events level reduction was also consistent with our previous the result. And then in summary, actually, our the efficiency evaluation shows that about 30% of the data reduction on average for a specific type of the work, we could achieve 75% of the data reduction. And then we also try to evaluate the accuracy of the impact our approach in terms of the impact on causality analysis. So actually, for the edges that we care about, most of them are preserved and identical before and after the optimization. Okay, so yeah, in terms of our modification and the efficacy algorithms, actually was reasonably fast for our data set. It took only about 1 hour. And then actually without our modification, actually the original epic growth data set didn't converge. Okay, so observations. Our approach is lossy compression algorithm. Therefore, we could achieve the very good compression rate. But what we did was that basically we only omitted the ordering information between the files within a very specific timeline. So therefore, we don't think that affects the accuracy of the causality analysis or forensic analysis as a whole. Okay, let me conclude our talk. So we propose a data duplication approach to support the on-demand forensic analysis. And then we also found out that our approach has a little or no impact to the causality analysis, and then it maintains the on-demand access to the data. And then this is in a high level, so a simple idea that scales the forensic analysis in action, actually converting the actual system problem into the well-formulated data mining problem. So average data reduction gain was about 28%, and in maximum case, it was 75%, 75 times. Okay, thank you.
Hi, really interesting work. So one way an attacker might maintain persistence on the host or sort of covertly, install malicious stuff would be to overwrite one of these malicious shared object libraries with a malicious version of libc or something like that. So does NodeMerge account for that? What happens if there's a new flow into one of these read-only files?
Actually, that is a really the good point. That's the reason why we only care about the read-only files. Whenever we also actually monitors the file write events. Whenever there is a file write events, we exclude them from our the analysis. So that is actually file writing activity is a very, very critical thing that we want to watch. Yes.
Can you give an example of a case where this node merging and data reduction would not help forensic analysis?
Actually, this approach is basically works well for I didn't have a time to mention it for the Linux systems than the Windows, because Linux is more friendly to the short-lived processes, and the Windows case is more for the long-running service model. And the users from the Windows systems are not handy with the scripting and their own jobs. So in that case, actually, we see the less reduction. So this is typically favorable to the environment that invoke and schedules a lot of the processes. Yes.